Hello and welcome back to our discussion of icing. Right now we're talking about structural ice, and specifically we're looking at the thermodynamics of freezing. So how does water freeze on a wing? Well, it depends on a number of factors. Depends, of course, on the temperature. That's pretty obvious, but it also depends upon the amount of liquid water in the cloud, the size of the drops in the cloud, and then finally how fast the airfoil or the structure is moving through the air. So first, let's take a look at the temperature. Temperature is very important, and we're going to look at two temperature regimes. We're going to look at very cold temperatures, and we're going to look at very warm temperatures. So cold temperatures, we're going to look at temperature of -20. Now remember, you have supercool liquid water at temperatures between 0 and -20. As you get colder than -20, you tend to find more ice crystals, but there still may be some liquid water in cloud. So as the droplet approaches the airfoil, that white thing there is the airfoil, and that little round blue thing is a water droplet. It strikes the airfoil, and at -20, it'll freeze on contact. As a matter of fact, if there are a lot of little droplets out there, they will all freeze on contact. And the rapid freezing of these droplets does not allow the dissolved air in the water to escape. So you have little bubbles of air that are trapped within those water droplets. So of course the air or the water droplets will appear to be white because of all these little bubbles. And then also, as each droplet freezes, it does not kind of fill in the water in between the droplets or the space between the droplets. So you tend to have just kind of a bumpy structure that's white. And this is what we call rime ice. At warmer temperatures, such as -5, when the water droplet hits the wing, it freezes more slowly. So it tends to spread out. The dissolved air bubbles in the water tend to escape, so the ice tends to be clearer. You don't have all these little bubbles that distract or diffract the light. So instead of being white, it tends to be more translucent. You can actually see through it. And this is what we call glaze or clear ice. So here's the temperature ranges for the different types of ice. Glaze ice or clear ice tend to be found between 0 and -8. Mixed ice between -8 to -15, and rime ice at much colder temperatures between -15 to -20, and even down to -40 if there is any supercooled liquid water. Typically at temperatures colder than -40, all supercooled liquid water freezes even without ice nuclei, and you tend to have ice crystals exclusively at temperatures colder than -40. Now this depends upon the liquid water content, and we're going to talk a little bit about that. This is assuming kind of an average liquid water content. Now let's take a look at how liquid water content determines the thermodynamics of freezing. As you recall, liquid water content is the mass of liquid water in a volume of cloud, and typically expressed in terms of grams per cubic meter. So there are two conditions when you can have high liquid water content. Either you can have a very large number of small drops, or you can have a small number of large drops. So in other words, liquid water content can be distributed across many drops if they're small, or only a few if they're very large drops. Now, the amount of liquid water content creates two effects. Number one, of course, is the severity of ice, or the rate of accretion, which is also the type of ice. The type of ice, or the intensity of ice, I mean, not the type. And then finally, it also determines the type of ice. So let's look at both of these. First, with high liquid water contents, you have a lot of ice building up on the wing. So the intensity tends to be moderate or severe icing. Remember that the rate of icing is a function of the rate that it is accumulated by an airfoil. So if you're flying through a very juicy cloud that has a high liquid water content, you're going to have a high rate of accretion, and the ice that you tend to get intensity will be moderate to severe. Now, the type of ice or the liquid water content also determines the type of ice that you get. When we say type, we're talking about glaze or clear, mixed, or rime ice. So the amount of liquid water depends upon or determines whether you get clear, mixed, or rime. So think of it this way. As your airfoil flies through the cloud, it's picking up liquid water. If you have a really juicy cloud with high liquid water content, then your airfoil is going to be picking up a lot of water on the wing, on the airfoil. And that water tends to freeze at colder temperatures colder than 0 degrees Celsius. So during this freezing process, latent heat is released. Going from a liquid to a solid liberates some heat. Where does that energy go? That energy actually goes into the water, and it warms the water a little bit. So this freezing process tends to warm the water, and it keeps it at slightly warmer temperatures, not necessarily at temperatures above 0, but maybe just slightly below 0 degrees Celsius. So because of the latent heat release, that tends to allow the temperature of the water to warm up a little bit, and it doesn't freeze as quickly. It freezes more slowly. And what happens is during that freezing process, it tends to spread out over the wing, and you tend to get more of a glaze type of ice. So this typically happens at warmer temperatures. Normally, under average liquid water contents, we usually find glaze or clear ice at temperatures between 0 and -8. But let's say that the cloud is really juicy. Let's say it has a high liquid water content. If you have a cloud that has a high liquid water content, then the glaze ice will be found at temperatures colder than -8, maybe down to -10, maybe -12. And the reason for that, once again, is the very slow freezing of water because of the release of latent heat. So this typically causes run-back ice, and run-back ice is pretty dangerous. This happens when you're flying at high liquid water contents at rather warm temperatures, maybe -6, -8, something like that. And run-back ice, what happens is ice will form past the de-icing boots, and you'll start to get ridges of ice past protected areas on the leading edge. That can be dangerous. It's caused a number of accidents, specifically the Roselawn icing accident back in 1994 in Illinois, or Indiana, I take that back. Indiana was a result of run-back ice. As a result, it disrupts the airflow over ailerons and other structures on the wing and can cause instabilities. Now, if you have low liquid water content in cloud, then of course two things can occur. Number one, your rate of accumulation or the icing intensity will not be so great. A drier cloud means less water droplets, maybe smaller water droplets, so it's going to be a slower accretion of ice, which tends to produce a trace to light icing. And also low liquid water contents also result in a type of ice that does not release much latent heat. Small amount of liquid water content in cloud, when it strikes the wing, doesn't release much latent heat. So it really doesn't warm the wing or the water like you saw in the high liquid water content case. So with a drier cloud, a lower liquid water content, there's not much latent heat that's released, so the temperature rise along the leading edge of the wing isn't much. So as a result, the water droplets still freeze pretty quickly, and you tend to get more of a rime type of ice when the liquid water content is low. We looked at these temperatures before. We said that rime ice happens between -15 to -40. However, if the cloud is really, really dry, then you tend to see rime ice at much warmer temperatures. Instead of -15, you might see it down to -10. You can get rime ice. And that's only if you have a cloud that has very little liquid water content. So liquid water content and temperature do determine the type of ice that you'll get, whether it be glaze, mixed, or rime. Another thing that determines the freezing on the wing is the drop size. And this kind of leads to the similar analogy of liquid water content. We talked about how liquid water content determines the type of ice that you get on the wing. Remember, higher liquid water contents tend to produce run-back ice and tend to produce also glaze or clear ice. And of course, with big drops, you tend to have generally higher liquid water contents with big drops. So that will produce, of course, better collection efficiencies. You'll have severe icing, and of course, with all that water freezing, it releases a lot of latent heat. So it tends to freeze slower. You tend to get more run-back ice, and it's a glaze or clear type of ice. As a matter of fact, this is a huge problem when you're flying in clouds if you have these large drops. And remember, when we talked about icing certification, we said that airplanes are only certified for flight into clouds that have droplets that are smaller than 50 microns in diameter, or 0.005 centimeters or 0.05 millimeters. Anything bigger than that, bigger than 50 microns, are called supercooled large drops, or SLDs. And SLDs are a problem, and they produce severe icing, and airplanes are not certified to fly into SLDs. So conversely, if you have smaller droplets, generally smaller droplets usually also imply lower liquid water contents. And lower liquid water contents mean that the droplets freeze more rapidly because there is less latent heat release. And when you have a rapid freezing of water droplets, you tend to have more of a rime type of ice. The last characteristic that determines the freezing of the water is the airspeed, how fast the airplane is going through the air. And there are two effects. One is skin friction, and the other is adiabatic compression and expansion. So in other words, if you're flying really fast, let's say that you're flying at Mach 1, then your airfoil is going to heat up significantly. You're talking about SR-71s and airplanes that are Mach 2. They don't have much of a problem with ice for a number of reasons. Number one, they can usually punch through icing layers pretty quickly vertically. And number two, their skin friction tends to, of course, skin friction, we're talking SR-72s or 71s, skin frictions or temperatures, skin temperatures of 400, 500 degrees Kelvin. You're not going to get any ice on that if you're moving Mach 2. But if you are flying slower than the speed of sound, still there is some adiabatic compression as the air approaches the wing. So in other words, as you fly through the air, if you're flying more than typically 200 knots, I think that's where they assume that the airflow is no longer incompressible. Above that point, you can start to think about compressibility factors. So faster than 200 knots, you're going to start seeing, of course, some significant compression along the leading edge of the wing. In other words, as the air approaches the wing, it slows down, and that slowing, that energy has to go someplace. It compresses against the wing, and it warms up. So this is adiabatic compression, and we have equations that tell us how much it's going to increase. And I've calculated some of those numbers for you and put in a table here. So it's usually significant at airspeeds more than 200 knots. So if you're flying at 200 knots, you're going to bump in temperature of 5 degrees Celsius. So in other words, if the static air temperature surrounding the airplane is 0 degrees Celsius, because of the flow of the airplane through the air, you're going to get a rise in temperature of 5 degrees Celsius. So you may not have ice forming on the wings because they're much warmer due to that adiabatic compression. And of course, the faster you go, the greater the rise. So those are some things to think about when you're flying through icing conditions, how the ice freezes on the airfoil.